All right. This lecture is going to be really awesome. It's going to be over 12.4, integrating in polar coordinates. But before I continue, I'd like to remind everyone, either at home or in person, that we'll be having an exam over chapter 10 and 11, right? So that's 10.1 through 10.5 and 11.1 all the way through 11.8. These guys I've uploaded selected solutions for, but of course there's a myriad of solutions on the internet. So make sure to not only look at my solutions, but also if you just Google certain things, you'll be able to find a lot of answers. So, but make sure you're understanding the stuff. Make sure you're using those solutions to increase your level of understanding. Because you just write it down for the homework and the test rolls around, it won't be very good. This test is going to be slightly harder than the first test due to a twofold reason. One, there's more material, there's more sections. And two, the material is getting a little harder. So, but I will again include bonus points at the end. I will again include bonus questions, and they'll be proof-based.
Guys, is it still going to be when we should be able to finish it within, like, whatever you said, I think before, it was like we could finish it within an hour and a half or something?
Yeah, but I will give you more time if you require it. I'll give you more time if you require it. I hope it can be done in an hour and a half. But, you know, this is going to be a longer test than that first one because there's more material to cover. There's probably going to be more questions on it. So, but I will give you guys a lot of time. Maybe not 7 hours, but I will give you like 2, 3, maybe 3.5. You know, it just kind of depends on how much you guys need and want. I'm flexible. I'm willing to work with you. Now, moving on. Remember, in polar coordinates, we can describe something where it required an x and a y. Now we can describe it like so. An r and a theta, where this is theta and this is r. So it's a way of describing two dimensions. So we have to define a polar rectangle. Okay, it's the set of r theta and r2 such that the radius ranges from A to B and the angle theta ranges from alpha to beta. It creates a polar rectangle, if you will, something like so. Okay, where this is just some d theta, this is just some dr, right? Actually, this is your r, this is your d theta, and this is your dr, just a little piece of r. And you'll notice that this right here is a r d theta. And why is that? Well, you can create a triangle, right? Here's d theta, here's x, and here's y. I claim that y is r d theta, and here's y. Let's take the sine of d theta. That's opposite over your hypotenuse, which is your r, right? So then multiply both sides by r, And that implies y is equal to sine of d theta r. But d theta is relatively almost equal to 0. So we take the small angle approximation. The small angle approximation. This says that for theta, very small, that the sine of theta is equal to 0. That makes sense, right? Sine of 0 is 0. And sine of 0.0001 is basically still 0. So if your angle is small enough and the d theta is like the tiniest angle you could think of, that means the sine of d theta just becomes d theta. And so our y is d theta r. So now when we take the product of dr and r d theta, we get a differential area, which is r dr d theta. So that's what this little small differential rectangle or square looks like. It's a small little piece of a rectangle. It's a small little piece of an area. That's how we're going to transform our integral into polar coordinates. But let me elaborate on that. So our rectangle R, when we zoom it into a bigger picture, okay, that's this region R right here, where this A to B, and this is angle alpha, and this is angle theta, okay? Then we can notice that in this region R, one tiny slice right here, we can call this some R of ij, some tiny area, where it equals to some R of I star theta of j star, where we have chopped up these intervals, A to B and alpha to beta. They have been chopped up. Where a delta R is equal to your B minus A over 2, and a delta theta is equal to your beta minus alpha over 2. How did I say over 2? What I mean, not necessarily over 2, I mean over m and n. I'm not cutting it in half, I'm cutting it into infinitesimally small pieces. Okay. Because we're going to take the limit as m and n approach infinity. That's what we're going to do. Okay. So we chop this interval up. We chop this interval up. So that means this interval right here gets chopped up into some r of I minus 1 to some ri. This, some theta of j minus 1 to some theta j. Where now these guys, Ri star is the same thing as Ri minus 1 plus Ri divided by 2. And this theta j star is the average of the j minus 1 and the j piece of this chopped up interval. Okay. So then this R of ij a set of R theta, an element of R2, such that this Ri minus 1, let's set it equal to Ri, and R theta j minus 1, let's set it equal to theta, let's set it equal to theta j. Okay. Or we define Ri star, R theta j star. Those are just the average points. If this is R, if this is Ri minus 1, this is Ri, this is and this is your theta j minus 1, and this is your theta ji. The star is like the average, so it's like right here in the middle. Okay, that's what's happening. We're just trying to be as general and as average as possible to get the best approximation. So a differential piece of area, area, is your area I minus area I minus 1, right? So this is the same thing as the area of a sector equation. I can factor out a 1/2 delta theta to get. Oh, but notice that this breaks down to Ri minus Ri minus 1 times Ri plus Ri minus 1. All right. Notice that when you distribute this 1/2 here, you get what we had. Did I delete it? Yeah, I did. I did delete it. Ri star was Ri plus Ri minus 1 divided by 2. When you distribute this 1/2 to that, you get that that's Ri star. And when you think about this, you get that that's just delta R. This is delta R. This is Ri star. So this is 1/2 delta R, delta theta, Ri star. And that's just a change in area, which is going to become a differential area when we take the limit as m and n approach infinity. So let's do that. So a little piece ranges from I equals 1 to n, j equals 1 to m of our function f of Ri star cosine of theta j star Ri star sine of theta j star. Okay. Times this differential area, not differential yet, just the delta area. We will turn it into a differential soon. Where did this come from? This comes from f of xy. But the transformation equation is x is equal to r cosine of theta. Y is equal to r sine of theta. So I spent enough time on the derivation here. What happens when you take the limit as m and n approaches infinity? All this is when you get our tool that we want, which means the double integral on a region of some f of xy, d some differential a, is the same thing as an integral from alpha to beta, integral from a to b, of some and I explained where the differential comes from. So your f of r cosine of theta, r sine of theta, r d theta. Remember this piece? That comes from the transformation equation of dA equaling r dr times d theta, which this is actually the same thing as a dx as well. This is when I use the sine of d theta argument, and I just rearranged it. So, without further ado, let's do a problem. So when you take the limit, these deltas become d's. That's really the rub. of calculus. Let's define a region such that y is positive and we have something ranging like so. So this makes an upper half annulus. An annulus is like a ring, kind of. But this makes an upper half annulus. Here's our y, here's our x. Y being strictly positive means we just take the upper half. Two circles with radius 1 and 2 mean that we wish to integrate this thing. Our region R is this shaded region over here, where clearly this is 0, 1, and this is 0, 2. So we can consider this as like a type 1 or a type 2 region and integrate it. But we shall be doing so utilizing polar coordinates. And the integral we wish to calculate is this one. Okay. Let's transform this integral into a polar coordinate integral, meaning I want to range from our theta. Theta ranges from 0 to pi, 180 degrees. And what does our radius range from? It ranges from 1 to 2. What is our function? 3x plus 4y squared, r d theta. And we got to remember to transform x and y. I'll remind the class of the transformation equations from rectangular to polar. Meaning this is the same thing as 3 times r cosine theta plus 4 times r sine of theta quantity squared. And the whole thing is being multiplied by r d theta. So this breaks down to parentheses 3r cosine of theta plus 4r squared sine squared theta times r d theta. So then this becomes integral from 0 to pi, integral from 1 to 2. Let's distribute that r. This becomes 3r squared cosine of theta plus 4r cubed sine squared theta dr d theta. Can't delete the picture because that's really important to see what we're integrating. Everything going fine so far?
I think so.
Good. I am pleased to have such astute students. Okay. So now let's actually integrate with respect to r. Integral 0 to pi. Now let's do the integration. It just thinks everything with respect to theta is a constant. So this becomes 3r cubed over 3 cosine of theta plus 4r to the 4th over 4 sine squared theta theta. Evaluate it at r is equal to 1, r is equal to 2. Okay. Cancel, 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 cancel. This is integral 0 to pi. When we plug it in, this becomes when you plug it in and you evaluate, I'm going to skip those steps because they take a long time. We get 7 cosine of theta plus 15 sine squared theta d theta. And then we distribute this integral 0 to pi of 7 cosine of theta d theta plus integral 0 to pi of 15 sine squared theta d theta. All right. Then we know that to integrate sine squared theta, we want to say that this is equal to 1/2 times 1 minus cosine of 2 theta. Okay. Then, once we do that, we can do u substitution. And once you do u substitution and integrate for both of them and evaluate, we get that this integral goes to 0. This integral over here ends up becoming 15 over 2 times pi minus 1/2 sine of 2 theta, evaluated from 0 to pi. And so this actually breaks down to just being equal to 15 pi over 2 once you do the evaluation. So that was this area of this analyst, that is.
Measuring area of annuli in this classroom.
Yes.
Okay.
Half annuli.
Just this once.
Half annuli. Now it's on to volumes. Let's do a volume problem. Let's find the volume of the solid bounded by the plane z equals 0, technically the xy plane. And let's say the equation z equals 1 minus x squared minus y squared. Okay. Notice that if z is equal to 0, then you can say this, and then algebraically solving, you can say this, and then that's a circle of radius 1. Okay. But notice that if we just didn't have anything to do about z, this would be a circle of radius 1, and if z was free, it would form a cylinder on the z-axis. But that's not the case. Z is governed by this equation here. And what is the range of some function like this? This is equal to a function f of xy, which is equal to z. So what is the range? Well, when you look at it, you see that the highest value this function can assume, because no matter if we plug in negative or positive numbers, when we square them, they become positive. And when we subtract them from this value, it decreases. So the highest value this thing can assume is when x and y are 0. Okay, the highest value. So, and it includes it, so it's 1. And then the lowest value you can assume is anything. It goes without bound. So the range is negative infinity to 1. However, our problem restricts us to values of z and above, z equals 0 and above. So our problem is restricting the range from 0 to 1, where z is an element of this interval. Are you familiar with this notation, z is an element of?
Yeah.
Yeah, it just means it's like z can range from 0 all the way to 1. That's all that means. So that means we have something that starts off as like a circle of radius 1, but it is constantly decreasing in value all the way up to this value z equals 1. And notice that when z equals 1, you get this equation. And so I subtract 1 from both sides. Divide by negative 1/2, and I get, what is this? It's a circle of radius 0, all right? So when z is equal to 1, I get a circle of radius 0. So over here at 0, 0, 1, I have a circle of radius 0. Down here, I have a circle of radius 1, right? So what forms is actually like a dome, like that. So we want to find the volume of this dome. That's what's going on here. So then that is equivalent to so it'll actually behoove us to utilize polar coordinates in this situation because this problem has cylindrical symmetry, polar symmetry. Circular symmetry. It's symmetric about rotations about the z-axis. Okay. So that integral over there is the same thing as how do we deal with theta? Theta goes around the whole circle. So it goes from 0 to 2 pi. How do we deal with our r? Well, r ranges from, because it's a solid, it ranges from 0 to 1. It's a solid and it sticks out to all these points. So to fill out the solid, the r ranges from nothing at the origin to 1 at the highest value of the points on the dome. And then we just reproduce our equation. And then we do our transformation equation. Do not forget to put parentheses here. You guys are advanced enough students to realize that, but it's easy to forget that r dr d theta is multiplied times the whole expression. When we write dA over here, it's multiplied times this whole thing. Yeah, I know you're not my pre-calc students, but yes, do not forget that. It's worth a mention. 1 minus r squared cosine squared theta minus r squared sine squared theta, r dr d theta. Notice that when we factor out r squared, I get this is cosine squared theta plus sine squared theta. And when I said factor out r, I meant a negative r. And so if I factor out a negative r, this becomes a plus, doesn't it? No, it doesn't. No, it doesn't. Because this was already plus, so this is the minus out here. Messing it up. Okay. Yeah. This is 1 plus negative r squared plus negative this. So we factor out a negative r squared, so these become pluses. But that negative r squared is still there. This is a Pythagorean identity. This becomes 1. So our integral is reduced to just 1 minus r squared. The integrand becomes integral 0 to 2 pi, integral 0 to 1 of 1 minus r squared times r dr d theta. Integral 0 to 2 pi, integral 0 to 1 of r minus r cubed dr d theta. Integral 0 to 2 pi of r squared over 2 minus r to the fourth over 4. Evaluate as 0 to 1 d theta. Whenever you do this evaluation, what do we get? Whenever you do this evaluation, You get that equal to 4th. And so when you integrate a 4th with respect to theta, you get 1/4 theta, evaluate as 0 and 2 pi. This becomes a 4th times 2 pi minus 0. So this becomes pi, 2 pi over 4, which is pi over 2. Any questions so far? Yeah, integrating that using polar is the way to go. If you tried to do it using rectangular, it wouldn't be as smooth.
So how do you decide, like if it doesn't give it to you in the problem, how do you decide what to do?
That's an excellent question. It all has to do with symmetry. So let's say like you want to like integrate what is the volume of two, like inside of two spheres. Then you do spherical integration. We haven't talked about that yet, but you would do spherical because it just makes the calculation, integral calculation, a lot easier. You get terms dropping out because of the Pythagorean identity. Let's say you want like a cylinder problem. You want to calculate the volume of a cylinder or the volume of in between a cylinder and a larger cylinder, stuff like that. You'd use polar. When we do an analysis, that's really when we're doing the half analysis. It's really it's conducive to using just the R and just the theta. Trying to parameterize that using X and Y is not as simple. It's just not as simple. The integrals are a lot harder. So you would have to see for yourself. Try and do this integral in rectangular. It's possible, but it will take a while. And some of them actually are just really, really hard and not worth spending your time on. Your time could be better spent doing other stuff, right?
Yeah.
That's how mathematicians think. They're like, well, we're all gonna kick the bucket soon. We might as well use our time wisely and invent as much mathematics as we can to leave a mathematical legacy, right? But if I'm calculating integrals all day, no one cares. That was a cool thing, let's say 300 years ago. 500 years ago, but like not anymore. It's still a cool thing, but it's not revolutionary. Okay? Here's another condition. If f is continuous on a region D, then we can actually say that this integral we can say that these boundary points can be functions of theta. So they used to be alpha and beta, but alpha and beta are just real numbers. So we can have a function of theta that evaluates to those real numbers. Could we not? Because for every theta, you can input it to a function and I'll output another theta. So this becomes h1 of theta, h2 of theta, f of r cosine of theta, r sine of theta, r d theta. Okay? That's just the last thing I have for today. So it's time for a quiz. Let's think of a quiz. What's some of the stuff we've been talking about? Okay, quiz. Must be a one question quiz. Calculate this integral. One, two, three, four, five. 1, 2, 3, 4, 5. That's it.
Is that just a one?
Yep. I put it there so it's not ambiguous. It's just the quintegral of 1 dx dy dx dy dx. It is a iterated integral. Don't worry about your integration constant. Yeah.
That's the only thing I was worried about.
I can read your mind, Jamie. I'm a telepath. Don't worry about the integration constant. Just show me that you guys can handle iterated integrals. And you guys at home, I'm expecting your solutions in around 15 to 20 minutes. In my email. Thank you. Good work. Luck in chemistry, although you don't need luck.
Thank you.
You just need math.